just recap a little bit, just to set the stage for what we're going to discuss today. So last few times, we basically discussed, roughly speaking, this broad class of puzzles related to black holes and how they get connected to, and we'll discuss a little bit about how they get connected to closed universes. But broadly speaking, we discussed that there were three scenarios that we were roughly classifying things into. There was the scenario which was the firewall scenario, which is to say that the interior of a black hole doesn't exist in some sense, effectively it completely breaks down. There was another scenario that we didn't discuss too much, which was this. So remember that there were a few assumptions that went into these puzzles. One was, of course, unitarity, and we're holding unitarity fixed. So we're assuming that the black hole S matrix is defined by some unitary S matrix. So then we could get rid of the equivalence principle, or we could get rid of black hole thermodynamics in some sense. So the other assumption that went into it was that the black hole entropy is some finite thing given by A over 4G. So it could be that somehow this is not the case. This, broadly speaking, would be, I like to call this statement AdS not equal to CFT. And we'll be more concrete about what exactly that means. So this is a scenario that we haven't discussed much at all. The other scenario was trying to get everything to work somehow, like as good as possible. And that was all of these versions of complementarity with a few stars. So we considered different versions of complementarity and tried to push how much we could try to achieve while still having all three of these principles holding together. And we saw that we're getting pushed towards issues with complete breakdowns of effective field theory in situations where we may not expect.
Double star, what again?
Sorry?
Double star.
So complementarity was just the initial version where you just say that you just describe physics in some patch. Complementarity star was when you now say, oh, you can do complex operations that spoil effective field theory, but you put an additional complexity count. Complementarity double star was when we stopped describing things in terms of a patch as such. We just said work with QFT on curved spacetime. But now you put in this new rule that there's a non-isometric map from the QFT on curved spacetime Hilbert space to the fundamental Hilbert space. And then there was this question that we were discussing of what's the relevant inner product to describe physics of the observer. But if you believe AdS equals CFT and the CFT inner product is all there is, then you're forced to this non-isometric description. And then there can be large fluctuations to that in certain situations.
I even come back.
Yes.
We even come back to 2 at some point.
So this lecture is about 2. That's why I was setting the stage, because so far we ignored 2, and largely there's some history to 2 as well, like because that has been discussed a lot in the literature, but it sort of died down, but it has picked up a little bit in recent times. So that's why I wanted to keep that for later before we discuss everything else. So this lecture is going to be all about 2.
And is 2 the idea that the entropy of the black hole is larger or smaller?
It's larger, yeah. So as we saw before, that the whole issue with the page curve was that the effective field theory degrees of freedom are too big to fit in a black hole, because if we think that the number of degrees of freedom is just A over 4G, and that was where all these issues were coming from. We have this non-isometric map from a huge set of degrees of freedom to a smaller set and so on. And one way to get around that is to say that fundamentally, you aren't in this small Hilbert space. There's actually a much bigger Hilbert space describing it. We'll see what that really means. Yeah.
Can you again say how does the issue of complementarity star gets resolved in complementarity double star?
It doesn't. It just so the issue with complementarity and complementarity star and so on was partly that it wasn't too precise. Like we were trying to say, we tried to describe infalling observer physics and stuff, but it wasn't so clear how that gets embedded in the fundamental theory. Like finally, we imagine that there's one fundamental quantum gravity theory that's describing everything. And it wasn't so clear how that was working. So with these calculations based on islands and the sort of stuff we discussed about how effective field theory states can appear orthogonal, but in the fundamental description, they are slightly non-orthogonal. Those sort of things help make complementarity double star much sharper. So complementarity double star in that sense is a sharper description where you make a very sharp claim. There's an effective field theory Hilbert space and there's a fundamental Hilbert space.
My question is about this new bound which we got in complementarity star.
Yes.
where it is gone in complementarity.
It is there. So what happens is, so let me just remind you a little bit about what happened here. In this situation, we had this map from HEFT to H fundamental. Right? And this was much bigger and this was smaller. This was given by e to the over 4G. And the idea was, so then there was this question we were discussing of which inner product is relevant, right? So if we want to say that the infalling observer is described completely by the fundamental description, so it's just by the CFT inner product, then everything physical is computed here. So then you can ask, how is this consistent with the description of a much larger set of degrees of freedom? And the idea was, as long as you stay within the complexity bound allows you to access only a much smaller set of states. Right, so this e to the a over 4g is some number of states, and then among those, the simple states is a much smaller subset. The complex, like the full set of states, involves a lot of complex states. So if I put a complexity bound, that basically allows me to access only a smaller subset, and then that is sufficient in the sense that if I access only a small set of states and a small set of observables, everything you compute here is roughly consistent with everything you compute here, as long as the black hole is big. So it's a sharper version of that complexity bound, where you say what exactly it means to impose this complexity bound. You impose some specific bound, and then you say that up to errors of order e to the minus a over 4g, everything you compute here is the same as everything you compute here, as long as you stay within that complexity bound. So it's a sharper version in that sense.
And for smaller black holes, EFT.
Yeah, so that's we'll get to that eventually. So of course, since we said that the errors are of order e to the minus a over 4g, if a is small, then you have to worry about this thing. So small black holes, in particular, we talk about closed universes where a is really C.
It's pretty big correction. Sorry, you must get on. But I wanted to ask you whether there is a fourth possibility we haven't talked about.
Yeah.
And just to say, it has come up in the course of many years. First from Ashok and then variants of that from Surat now, I think, which is maybe what was not right in the complementary way of thinking, at least where you once said, how can you have stuff inside as well as outside, was an implicit feeling that the Hilbert space should factorize. And actually, the Hilbert space cannot factorize in a precise way. And therefore, you can't make this statement precise, that there's some big contradiction between things being inside and then how can they be outside, And a variant of this just for entropy is that the entanglement, if you try to compute it, in any effective field theory kind of way, comes out to be infinite. In string theory, we believe that it should be finite, but if any theory gives it to be finite, it should automatically, not have this split property in some very nice way. Okay, those are not core, but is that a possibility that Surat, for example, now really emphasizes this, right?
Yeah.
The lack of the split properties at the root of why you're able to sit at infinity and recover everything.
Yeah, I mean, underlying some of these discussions is clearly the fact that we assume that there exists something like a page curve, and you can ask this question at all. At this point, there are pretty concrete versions of the page curve. I think even Subrat agrees with this. They wrote a recent paper where they basically, they agree on the fact that there exist page curves for certain subsets of certain subalgebras that you can very sharply define in situations like AdS, CFT, and so on, where it's very clear that you can define an entropy and that entropy follows a page curve and that page curve is given by an Islands calculation. I think the dispute is largely about maybe the relevant question is when you have the full boundary, it's a more limited setting.
Keep the Hamiltonian as well.
Yeah, it's some very specific algebra, which is the whole CFT algebra. If you say that you have access to literally everything in the CFT and there's no, it's some all-powerful observer, then there's no page curve at all because in any pure state, the entropy just always stays zero. Everything is unitary and you started with a pure state, you end with a pure state and nothing went wrong in between as well. It's just completely unitary evolution. So instead of a page curve, you just have entropy being zero all the time. But I don't know if that, I guess the dispute here is whether that accurately models what we would do if we try to do this experiment. Do we really have to keep track of the Hamiltonian, etc.? You could imagine, it has been argued that you could try to do this experiment in ways where you're more limited, where you have access to only certain set of degrees of freedom, not the whole set, including the Hamiltonian, for example. And then there certainly is a page curve. I think there's agreement that there is a page curve and it comes from islands, and all of those things still hold.
Is that still true that, I mean, is the idea that you can reconstruct the entire interior just from data?
So if you believe entanglement was reconstruction, so if you believed that any of the other page curve calculations say anything about reconstructing the interior and all of that, entanglement wedge reconstruction, Pets map, etc., then you have to say the same here. Like there is really no difference.
And so you have to say, since you have all the information,
Yeah.
if you keep the whole algebra, you can reconstruct.
Yeah, then you could have just always done it anyway. Like then you would just say I had access to the full CFT, so everything is in the full CFT. So I could have done this at any time anyway. Like I didn't have to wait for the black hole to half evaporate or whatever. I could have done it when it was like 1/4 evaporate.
You should go on, but I just mean, so you throw the Britannica in some colloquial sense, at least it's coming out while it's still inside.
Right.
But in another view, if
it was just always
algebra, at infinity, it was always there at infinity, but you can also explain why it's inside and outside in the bulk at the same time. I mean, is that something?
I mean, I guess then you would
to say
in that language. I think what they would say is that there's really, I mean, because quantum gravity is kind of non-local in the way you said, things don't factorize. It's okay to have it in both places. It's like what we said about the cloning paradox, which is that yes, it looks like it's there in two places, but these are secretly the same degrees of freedom, just in a scrambled form. So it's
because there's no factorization.
There's no factorization. It's basically like saying complementarity. Like these are the same degrees of freedom, just jumbled up. You should talk of them as separate degrees of freedom.
Sorry, please go.
But I still think like whatever we've discussed so far in terms of islands, and in fact, I think Surat had a paper maybe this week or maybe last week where they essentially agree that there are all of these situations where islands play a role, and whatever you say,
is the idea that you look at only the news operators?
Yeah, so there's different situations you can consider. That in the flat space case, you ignore the Hamiltonian and
the news operators form a closed subalgebra.
Yeah, you do that, or actually related to what you were suggesting the other day, you consider these plasma ball-like situations, and then you just look at the algebra of the CFT, which is far away, where you think you've collected all the radiation and that. So they try to argue that this is like just conjuring up a page curve because you chose to like put a, it's like they call it putting blinders on. Like it's like you forgot to look at something, like you chose not to look at something, and that's why you got a page curve. I think that's a matter of perspective, but I think like if you think that's a physical
blindness in the plasma ball situation is
you ignore some region, but physically it looks very much as you were suggesting that like that's like Hawking radiation coming out. Someone has access to it. There's a very sharply defined subalgebra, which we would think of as capturing all the stuff that the radiation knows about, and then there's a clear sense in which that has an eye.
Thank you. So, and just one maybe for something. Is there any, suppose, I mean, we could do semi-classical quantization, right? And try to quantify the extent to which semi-classically this product structure breaks. Is your sense that is very hard?
I think, okay. In situations where you have like non-trivial stuff happening, like you've broken enough symmetries and so on, so it's like a generic background.
Yeah, it can't be very large then.
It can't be very large, exactly. There's operators which are just localized to that, at least to all orders in one over n. To that stuff, yeah.
What did you guys?
Yeah.
Sorry. I'm going to say any attempt to do it might suggest that it's actually, I mean, the extended Hilbert space would be very large, right? Because at every, it is the way it works in gauge theories, is that, if you try to discretize it, then at every link, you have extra degrees of freedom across that link, which you entangle.
Yeah.
And so, roughly you have an area worth of extension of the Hilbert space, right? So, I don't know whether you want to count it large or small, but for, if it's an area in units of Planck, it's the entropy worth of extension, So it doesn't look small if you're trying to explain the entropy area worth of final answer.
But I guess if you talk about just observables restricted to like that you think are localized to some area and whether they commute with stuff near the boundary, into all orders in 1 over n or to all orders in G, if you're in a sufficiently generic background, that can be done. Non-perturbatively, I don't think you can. Non-perturbatively, things won't commute. There's
No,
a good
the local
approximation
nature
which you
of
can
the
do that.
algebra will be, if the question was, if you're trying to ask to what extent the Hilbert space doesn't factor, right? What was that?
Yeah, but to what extent you can have something here which is completely independent of something.
Yeah.
Oh,
Like the split property.
To what extent do actual operators commute?
Yeah.
Yeah. Gauge invariant operator. Yeah, that would be very.
Because complementarity would say that that structure completely breaks down. Right. So it's a much more serious thing than having some boundary kind of mixing.
Yeah.
And I think I agree with Pratik that maybe there are special situations like near the vacuum of AdS or something where.
Yeah, I think if you have symmetries, then you have to be careful about these things because, for example, gauge invariant operators have to respect those symmetries. They have to be invariant under symmetries. So you can, like in pure de Sitter, for example, you can only have things which are rotationally invariant. So, but if you have enough stuff there already,
expect approximate locality of effective field theory to break down, except for exponential subrest effect.
Right.
You might tell us the
That's so then this is the claim that while it may be true in some exact way that the information was always there, semi-classically we'll never see it. Insufficiently in all situations. Yeah.
Right. Okay, so maybe they're all saying the same thing, that you do sufficiently complex things to access parts of space-time, which are very far away.
It feels like you need to access not the gravitational degrees of freedom, but the gluons. Roughly. Right. Once you have the gluons, you know everything.
Yeah.
Okay.
Gravity climate, you're saying that just semi-classical quantization around space-time is not good enough. You need topology.
Something like that.
But if suppose you try to construct a structure of the Hilbert space, that structure of the Hilbert space, at least. I see. So you're saying, well, now once you include the wormhole variables. Yeah.
Those are in some sense the non-productive.
But I mean, I think what you're saying is what I would say, that if you try to construct a Hilbert space, you might at first say you can do it entirely in terms of gauge invariant operators. Okay, but the lesson coming out of gauge theories is that you have to think of the gluons, because you ultimately have to think about how to factorize that Hilbert space in some extended way, and that requires so I would agree with that summary of
and this is the lesson anyway. I mean, in some sense, from AdS. But certainly,
if you have access to like finite stuff,
you create a truck in the middle. You do whatever you want. But it's hard with low-lying twists.
Yeah, I mean, I think even these situations in vacuum AdS that they discuss is largely like you think about the stuff you just said. Like you can act with some complicated operator in the CFT and then create a truck in the middle. Equivalently, you could imagine just some near boundary observer who has access to complicated operators and they just do some order n squared product of these slight things and so on. And then that is effectively equal to creating a truck in the middle. So there's really not much of a difference between a truly boundary observer and a near boundary bulk observer who can do things like that. That's like having access to the gluons. And in that case, it's true that these operators are basically secretly the same and there's a complete breakdown of locality.
Right. You're saying anything range and anything I can make out of the gluons, I can also make out of traces.
Traces and
once I go right.
Exactly.
Maybe there was a
Sorry. I had a related question. So one of the things maybe you said in response to the discussion that just happened is that one can get the page curve if one doesn't look at the Hamiltonian, right? Whether it is in the AdS CFT context or in asymptotically flat spacetimes where you just keep the news operator algebra. But I was wondering, an argument seems to be that if you looked at, let's say in the asymptotically flat spacetime case, if you looked at gauge invariant quantity, like the Riemann tensor, that has in it both the metric, both the news tensor and the Hamiltonian. So how do you keep one and not keep the other? And in case of AdS CFT, if you drop the Hamiltonian, then you generate it by taking OPE of, of other primaries that you have. So the stress tensor comes out in the OPE. So how do you keep these and don't keep the stress tensor? So is there a consistent way to in either of these settings to keep one and not the other?
Yeah, let me talk about the AdS CFT case because I understand that a little bit better than the flat space case. We can discuss that afterwards. In the AdS CFT case, I think you're imagining something where you have access to the full boundary, but you somehow want only a limited set of operators. That's the kind of situation you're imagining?
Yeah.
Yeah,
That you somehow don't keep the stress tensor right in the CFT.
Right. So I think the cleanest example that I find is what Shiraz was suggesting, which is that there are these situations like these plasma balls where effectively what happens is you have some region where there's a localized black hole which is radiating, and in the CFT there's I don't know what picture to draw, but you could imagine that there's some small region where the black hole is localized, and then everywhere else is where the radiation is getting collected. So you can consider the sub-region of the CFT where all that radiation is getting collected and try to compute its entropy. That's a well-defined algebra already, and it's a well-defined entropy. So there you don't have to worry about this thing about different operators giving you the Hamiltonian. The Hamiltonian could possibly be in that algebra because it's not the full bound. Now, there's a question of whether that is physically a good model for what you would do if you were trying to measure the page curve. And that's where I think this dispute lies. But certainly that algebra is well defined. Right?
So you're saying you keep a part of the boundary. You keep like some part of the boundary, but not the full boundary.
Yeah. I mean, initially, I mean, one of the ideas related to this was simply imagine that you have a black hole in AdS, which is somehow in this strange situation. I think this has been said in different ways. Like you can imagine there's a mirror on one side so that all the radiation comes out and then gets collected on one side. Something like that. So that there's no really Hawking radiation on the left side of the pore, it's all on the right side. And then having access to a region like that would give you essentially access to all of the radiation. And that's obviously a well-defined algebra and gives you a well-defined entropy. Now, then there were complaints about whether such a situation exists and so on. So I think this plasma ball construction is a concrete construction where you can just see it exists. Yeah. So the thing you're missing in this case is stuff that was on the other side. But semi-classically, none of the radiation was getting out there anyway. So it seems strange to say that while trying to physically model the process of trying to capture Hawking radiation and see the entropy come out, you required some of that stuff where semi-classically there was really no radiation going there anyway. If you had access to that, then yeah, I agree that you won't get a page curve, but it's not so clear to me that that's the kind of experiment that you would do.
Mm-hmm. But for this, you're saying that you would have to, I mean, in some sense, you would have to, on the boundary, be agnostic to you would have to have access only to some small region of the boundary in AdS CFT to see this.
I think, so that's a good question. So roughly speaking, as you said, if you have access to all of the degrees of freedom, then of course it's a unitary theory, so entropy stays zero all the time. So of course, when we're talking about the page curve calculation, it must be that we're talking about some kind of sub-algebra of that full algebra in some coarse-grained manner. And this was usually vague, like we weren't clear about what that algebra is. And then we were imagining that when you squint enough, then you see this kind of page curve. In this situation, that algebra is very sharp because you can just talk about this boundary subregion, and that's a very well-defined algebra in the full quantum gravity theory. So this is like a sharper version of that.
But in the case of asymptotically flat spacetime, doesn't seem that I can even restrict myself to some region, right? Because even if I restricted myself to a region, it would seem that a gauge invariant quantity will have, it's like taking one part of one component of the metric and throwing it away and keeping another component of the metric.
But is there a problem with just the news algebra, isn't that?
It's a problem in the sense that, like, if I imagine starting off with gauge invariant quantities, like the news is one component of the metric, right?
Okay.
But if I imagine starting with a gauge invariant quantity, then I would like to start with like the Riemann tensor or something, right? And then it seems unclear because both of these come in the same Riemann tensor component. So then what am I saying if I drop one and keep the other?
Is also gauge invariant because it's as asymptotic infinity. It's radiation, you can measure it. So I mean, it seems to me that this is a well-defined sub-algebra, And you can say we also want that other operator, but within semi-classical gravity, that other operator is created using the Gauss law. It's created as a functional of the news operators. It's not really independent, right? It's not like, I mean, in the field, boundary field theory, it would be independent. But otherwise, it is another operator, but it's created as integral news something, right?
Right, but it is another component of the metric. So if I allow myself to take extrapolate limits of bound field of bulk quantities and say those are my boundary operators, then it seems that I need some new principle to say why I can take one operator and why I have to not take another operator.
Say the principle is that you want a closed subalgebra. There's a clear question whether the news operators form a closed subalgebra. At least let's agree on that. Yeah. There, the answer is yes, right? So you agree with that, right?
Right. Right. But
the answer to that is yes. So at least mathematically, one can ask the question of new, the entanglement of the early news and the late news, right? I mean, that's a well-defined question. Now you may say that it's not a very natural question. Yeah. Now that one can debate about, but at least if it's true that this calculation gives you the page curve, that is an interesting statement, right?
Right.
But right. A little bit more about what else one should be doing and should not be doing. But that is a very clear mathematical statement that somehow sounds interesting.
And I thought people agreed that if you didn't keep the Hamiltonian, just the news operators, you would.
If I understand the latest paper from Subrath and company, it sounds like they agree that mathematically this is a well-defined thing.
No, but just to say, I don't think there is any new argument either in that paper or in the earlier paper by Pennington and company on this issue.
Yeah,
because this is all it's just that they have been stating it again, but I don't think there's a new argument. It's just that, and I don't think anybody has really made a calculation in asymptotically flat space where they've derived the page curve.
So
it is.
There's some Marolf business which I don't understand, but
because when I was he said, if you leave out the Hamiltonian, they have not done it through calculation.
There is a replica trick calculation that people do, and I guess it starts from Hartmann et al., like Strominger and all. What you do is basically take some cut, put some twist operator here, and then take, imagine two copies of this, which are cyclically glued around that, look for saddle points for that. That ends up having a saddle point where there's some island-like thing here. That's the calculation that I know has been done. And I think originally it's Hartmann, Shagurian, and Strominger.
I think
and then Marolf and Maxfield did a similar calculation. And others.
And is it completely clear? I tried to read these papers and somehow never felt very clear.
The Andy paper, which is this RST paper, right? I felt it, at least we can look at it again, but I felt there were many gaps.
Right. Okay. There's some path integral calculation that's done. And I guess it becomes a question of, in the end, you have to define some algebra for which this is computing the entropy.
Yeah, and then replica trick calculation. Yeah. Maybe I missed it, but I was convinced they did it. Maybe I'm wrong.
Yeah, even I got that.
There's that RST paper with Hartmann and Andy.
And actually, Andy said this. He was not very happy.
The conclusion is written in a very, does it substantiate this, that, I don't know.
Anyway, but at least to whatever extent it's been done, is it clear that this calculation computes that algebra? Is that clear?
I don't see it.
So
at least I don't see it, but maybe other
issues. Okay, but I would love to, because if they've shown it definitively, because you mentioned this, that in any such 2D model, you can even asymptotically flat, no break between gravitational region and non-gravitational. We can prove islands. I'd love to convince.
It's at that level, It's at
but that would be great to know for sure.
I agree.
Just in terms of problems.
So I would say that the AdS CFT calculations are much cleaner just because we understand the boundary algebra so much better. But I think what has been discussed so far is, does there exist an algebra for which this is plausibly the answer, and that's this algebra that we're discussing, which is this news thing. I don't think the calculation in flat space is at the same level as the AdS calculation. So that's true.
So the second point that you said is whether this replica calculation is same as the news algebra calculation.
Is algebraically computing the entanglement entropy of the news algebra here with news algebra there.
The same as whether.
And that would be very nice to know, right? I mean, what would be really cool is to do the calculation to realize that there is a sort of subtlety, right? If you ignore integrating over one mode,
it's roughly like that. So that's the rough picture. I mean, you may comment.
I mean, that ignoring of the mode allows you to factor.
Exactly.
Otherwise, you'll just
if you add that mode, then you basically allow moving this twist operator wherever you like, and then you'll end up pushing it all the way to infinity so that you get 0, no matter where you start from. That's roughly the picture I have now. I don't know how sharp this is. It is roughly one mode, which is that cut. And that's the Hamiltonian.
Yeah, it would be nice to see the replica trick calculation opened out and see the choice. But good. This is a good problem to research. This was the problem I wanted. We should read this paper together. Strong interpretation.
Okay.
If Omkar will let you.
Sorry, I just want. I'm sorry to interrupt so much, but the calculation that both Subrat brought up in our meeting and Abhijit is thinking about now and so on, I feel conceptually similar. It's a bit like calculating within semi-classical gravity the entanglement entropy of half of this de Sitter sphere with the other half. So because
both say again, sorry, what is this?
de Sitter space.
Yes.
De Sitter space is a sphere that's evolving in time.
Right.
Now, if you were not holographic, if you were semi-classical, or if you were in a quantum field theory, and any spatial slides, you can compute the entanglement entropy of one half of the sphere.
Yes.
Okay, so you can try to do that at infinity. And in a quantum field theory, this should be extremely well defined.
Yeah.
In a gravity theory, this should not be well defined because the entanglement entropy is codimension 2, right? But one could once again set up the calculation, try to see what makes the issue.
One can set you up, but let me ask you this. At least when I thought about it, doesn't it give you an answer which is just the sphere partition function? Because the n replicated guy is still a sphere. And so ultimately, at least when I thought about it, the answer gets disconnected to the sphere partition function, which requires some definition. But if you're willing to put in an observer now we have a very precise definition of the sphere partition function. So
in a topological set, it may be topologically a sphere, but this is geometric.
No,
it's not because
it's to make the norm, then it would be a sphere.
but even the replica
trick,
because you get this branch covers, but ultimately
There's really only one solution, right? Like it's the sphere. Like what else?
That's what
Practically, at least you get different geometry.
So geometry is not a sphere.
We talked of that it's weird geometry that you get. But it's not that it cancels the Lorentzian cancel.
That's what maybe I've stood quick. I see.
You're at infinity, so geometry is frozen there.
And one nice thing about quantum field theory is that there is a check because you can do that on the Euclidean space and just analytically continue your branch points all the way up to the complex plane. And that will tell you what to expect. And then if one can produce that out of replica trick, that I think would be.
Say again, please. Say again.
No, I mean, the problem is phrased at late time.
Yes.
Right, about the entanglement of half sphere versus the half sphere. And one can do that. So there is a check where you can do that calculation just on the Euclidean space, right? With the branch points being on the boundary, the equator. And then, because it's just quantum field, you can maybe even CFT. I mean, you can just analytically continue then in complex theta, which is this global time, and go all the way up to late times. Right? We check whether
you want to do it in the full gravity theory.
No, first to begin with in
QFT.
Just to understand how the replica trick works in QFT.
In QFT, you get some different.
No, but out of you want to do it using the replica.
Yeah. That you can do, but that won't give you the sphere. But I thought you meant gravity.
No, just semi-classical that shit.
That you can do, But I thought something meant like in gravity, because that's really the only solution you find.
If you do it, I thought you just get the sphere.
That is even more complicated. I mean, it's like
there I don't know.
But in QFT also, it's not very
okay.
That's QFT in fixed pattern. Is that
semi-classical gravity, let's say.
Yeah.
Semi-classical gravity.
But full path integral.
Yeah, semi-classical gravity, like what is you doing? Like you have some orthogonal wave function on the metrics, and then how are you going to define them?
Yeah.
What is semi-classical gravity? I don't understand that.
The sphere at infinity is sort of frozen.
Yeah, it's frozen, but the full path in
It's a fluctuating metric sphere is really only a very short distance fluctuations are still fluctuating.
Yeah. I agree. I'm willing to put the boundary condition.
Yeah,
infinity, the full path infinity. Right? Maybe I'm still quick in the geometry is subtle. But
I mean,
it's a full gravitational calculation.
yeah, but the answer that I'm willing to live with is the leading order answer. That's what I mean by this and that's.
And the interesting thing would be to see to what extent semi-classical stuff can get it right or go wrong, right? I mean, I feel that's interesting.
Right.
I mean,
But do you think in quantum field theory this is just straightforward replica trick?
I would think so.
No, because it is at late times, it was a bit confusing for me, but maybe
The calculation may be tricky.
Calculation might be hard, but like in
But the calculation sounds complicated.
that may be complicated. I don't know, but yeah. I just think that conceptually it should be similar.
because that thing that you just have outlined at very far away
Right.
black space is kind of similar to what you are saying.
Right.
Because there is a non-gravitating
Right.
space.
There's another- yeah.
Another quantum field.
Yeah.
Okay.
Because it's
So otherwise, if you have a fluctuating metric, then you run into issues of what surface.
Right, exactly. Somehow gauge it very
And if I was reasonably control, we can in a reasonably precise way.
Yeah. Then I think it's just you have.
Yeah.
But so begin with just that first.
even there, sorry, I'll shut up after this, but even there, I think we should see that there's some issue. Like one mode you're ignoring or something like that, which tells you this is not really well-defined calculation. That would be very satisfying.
I think an easier version of that question is just take AdS. And so let's say we look at some. So normally we say we have a boundary subregion and there's an RT surface associated with that. Semi-classically, we could of course compute the entropy of any surface. You can compute entropy of that surface. That is some well-defined thing. And I've so far not seen anything go wrong with that definition. That would be great if we found that, but I don't know if we have. I'm just saying that here in gravity, what we do is in AdS CFT, what we do is fix boundary condition at infinity. That defines some subalgebra. We do the bulk calculation. It gives us well-defined rules for the bulk calculation, and the replication ends up happening around the extremal surface.
Correct.
So we know that the semi-classical calculation around the extremal surface is well-defined because it's computing something that is well-defined, the boundary entropy. But semi-classically, there's nothing wrong with computing the entropy of this division.
Yes,
And what does that mean on the boundary? We have no answer to that. But there is also nothing so far I've seen that goes wrong in that calculation. Like what is wrong with just doing that calculation?
In fact, that's the calculation that all these algebras people do. Right?
Yeah.
The recent developments of algebras and so on.
Right. There you can do all these. So I don't know. I mean, there is one thing that goes a little wrong, which is when you consider profiles like this, like you're basically replicating around this surface.
How do you mean? We'll talk about it. But you have to define that problem in a way that is.
Define gauge invariant surfaces which are not the extremal surface. Like for example, going so much distance from here.
Or you can just say K is not equal to 0, but
or K squared is 0 or something like that. There's many different gauge invariant specifications. Yeah, like that. Yeah.
But the answer
so that you can do. So you can define gauge invariant surfaces. But how to do the replica trick with that? I mean, there's one issue with it, which is that normally when we do semi-classical calculations in non-gravity, so you're just doing QFT, then this would just be some conical space-time on which you're trying to compute the action. That is, of course, not what we do when we do the replica trick around the Ryutakyanagi surface. We find this smooth solution and then analytically continue like Lefkowitz-Madison. The analog of those rules are not clear here. But there, that rule comes out because we're trying to compute a boundary entropy. In the bulk, if you just computed a QFT entropy, you would introduce a conical defect here and try to compute things. That's some different calculation. Whether that means anything is.
But if it's a quantum field theory, then there is no problem.
Then it should be fine. If it's a quantum field theory, you can literally compute that.
So
and it's like
the distinction between quantum field theory and a very weak input gravitational theory needs to be made.
Yeah, I feel that.
Yeah.
Because these people, that's what these are.
Because even in a weakly coupled gravitational theory, this is not a precisely defined surface.
No, you can define it precisely. I think that is the
calculation will change.
The calculation may change. There's a well-defined region. Like that I think is in principle well-defined. The calculation, I don't know if something goes wrong with the calculation.
I mean, the definition, anyway, I think we're going too far. But the JLMS appendix
Yes.
spent a lot of time trying to make precise sense of this thing.
Yes.
And it was important that it was an extremal surface.
No, I think JLMS got that appendix completely wrong. I think they tried to make that argument that extremality was important, but I mean, it's been shown later. Like, for example, Dong, Harlow, and Marolf have a discussion about this. That externality was really not important. You could have defined it in any gauge invariant way, and it was totally fine at that level, at the level at which they were working, which is just classical phase space, having a well-defined classical phase space.
It's a boundary condition and so on.
Yeah, so that one choice that works is extremality, but there are other choices that work. It wasn't really that important. So yeah, that's my understanding. So they really tried to make the argument that there was something special, but so far I haven't seen anything that's really special about externality from a semi-classical perspective.
My suggestion is that we can now.
Okay, so first line of my notes. So now what we're going to try to do is explore this option, and we'll try to see what it really means to try to explore this option. There's some certain formalism which makes it concrete, and this is this formalism that was introduced by Marolf-Maxfield. So this was a very interesting paper that appeared around the time of islands, and it gave an interpretation to some of these calculations, which was slightly different from many of the other calculations. But over time, it's been gaining traction because we're facing all of these issues with versions of complementarity and so on, and so people have tried to see what we can make out of this. So here's how you define. So their idea was to try to define a Hilbert space for closed universe. So remember, we already discussed that when we have the gravitational path integral where we're allowing all possible topologies. So one example would be, let's say we just use boundaries, and then we can connect them in various ways. Something like that. This would be one contribution that contributes to the gravitational path integral. In AdS CFT, normally we would think of as a product of partition functions. So let's say we have some sources here, J1, J2, J3, J4, J5. We would normally think of this as partition function, which is a function of these sources. And this would just be a number. But let's ignore that fact for now. We'll come back to it later. In the gravity description, this is a perfectly reasonable contribution to the path integral. And the way we want to interpret it is to cut it open in the middle and think about the state that it's preparing. So so we can now think about states that are prepared by adding in asymptotic boundaries. So we add in these asymptotic boundaries in the Euclidean past, which is J1, J2, J3. And then in the Euclidean future, we have some other J4 and J5. And the way we want to think of this calculation is as an inner product. We want to define this as inner product between J4, with right now, these Z's are just, you should just think of that as a boundary condition. So the Z of J1 is just a boundary condition, which gives you these sources J1, J2, J3. And then the claim here, so the way we're interpreting this path integral is as an overlap between this state that's prepared by these three boundaries and a state that's prepared by those three boundaries. And if we look at it in the usual sense where we cut it open in the middle, this thing, so these are asymptotic boundaries which are infinitely far. Normally in AdS CFT, we try to cut it open through asymptotic boundaries so that we define something like, say, vacuum AdS and so on. So where it has asymptotic boundaries. Here, there's no asymptotic boundary on the slice that we cut on. These are all, so this is basically just a circle. This is a circle and this is a circle. This is just a cylinder and this was some pair of pants that we cut. So this is just a state which looks like two finite geometries, two circles. And we're interpreting that as a state of two closed universes. So this is a state of what? This is a state of closed universes. Like, what do you mean by state? Is there any boundary? No. So we'll come to the boundary thing later. Like, so it's going to be hard to give it a boundary interpretation. I mean, there'll be some interpretation, but not in the standard AdS CFT sense. So right now, let's just think of it as a gravitational construction of the Hilbert space of closed universe.
And can you say a little bit more about it? As gravity, how is this state prepared?
So what we are doing is defining boundary conditions. That part is like the usual story. We define these boundary conditions and let the gravitational path integral fill it in with everything.
So like JT gravity with
It's like a JT gravity. So these will be fixed circles with some sizes. This will be fixed circles. And then we just fill it in with everything. There'll be many contributions to it, all of which, when we cut it in the middle, will have some closed universes living around. Even the number of closed universes can be different. For example, there would be some process which looks like it fused these things, and then this would be just one big circle. So there'll be contributions. So for the same state that we prepared, there'll be different contributions with naively different numbers of universes all on this slice.
And in string world sheet theory, this would just be the Fock space.
This is exactly. So this is very natural from the perspective of string theory. So you can think of these as past asymptotic states, and these are future asymptotic states of strings. They can fuse and interact and so on. And in the middle, we're just cutting it open and trying to see what's the set of states that we have. There, it's like doing string field theory, where you have states of arbitrary number of strings in the middle.
And in that situation, we could have looked at this Hilbert space at early times. It's just a Fock space.
Yeah.
Is that going to carry through in general?
So good. I'm actually not. Maybe we should question that as well, because that is the sort of thing that. So there's a long history to this sort of construction, and roughly speaking, what you just said is how Coleman was thinking about it. So Coleman had a similar construction where he was working with it as a roughly Fock space. The set of states can be defined like a Fock space, I guess, but it's very far from being free. So there's a sense in which they're free really far away, because there's a clear sense in which you can define the number of universes when you're really near the asymptote, but they interact heavily. So, okay, depends on what you mean by Fock space. Like it's a Fock space when you think about the asymptotic states, but like inside it's some scattering. Yeah, in that sense, it's a Fock space.
Can I just say, sorry, we haven't had a chance to talk about this, but in the work at least we did in JT and TS, there's a very precise sense in which the asymptotic states map to states in single universe Hilbert spaces. You know, when you quantize in the single universe Hilbert space sector, you have some choices, but one choice of quantization maps very precisely to, let me just complete, to the matrix model. And then you compute topology changing processes either with the gravitational path integral or with the matrix model, and they work, right? But what you have is a very precise map to the notion of states in canonical quantization for the asymptotic regions.
Yes.
Whereas the in-between region is actually a Euclidean configuration, you know, in the JT path integral. So at least I was not able to come up with a very precise notion of states by cutting the Euclidean path integral at arbitrary locations. The asymptotic things could be mapped in a very precise way, but not intermediate configuration, because you know.
The states that we're going to define here are going to be defined by asymptotic boundary conditions. So everything is going to be from the asymptotic Fock space. Then all I need to specify is the set of states and the inner product, and this specifies all of that.
And that's true.
That's all that's good.
It's just all I was saying was if we chop in the middle, then it gets precise notion. Then I couldn't come up with that.
So in this whole construction, you're only ever going to talk about asymptotic.
Then it's a very clear notion. You can just canonically quantize and.
No, but it's different from the canonical quantization in the sense that in standard canonical quantization, you might have just done, say, for example, non-topology changing things, right? So you could have just started
because it's asymptotic states, you can understand them very precisely in canonical quantization of single universe.
Yeah, but I mean, okay, I guess there's an order of limits sort of thing here, where like that same state will have topology changing processes in the bulk.
When they interact. But all I'm saying is, in the matrix model, you have a very precise notion of eigenstates of the matrix. And there's a one-to-one map between that and the states you get by canonical.
I'm just pointing out that this inner product is not unique. There was a different inner product that we could have defined, which was where we defined something like two boundaries or twin boundaries, and they always go this way. That's a different inner product, which I'm calling which has often been called a canonical quantization inner product. I'm just differentiating it from that. Okay, what you're saying is not wrong. I'm just clearing out terminology.
Sure. I'm not even associating an inner product. I'm just saying the transition amplitude as, just view the path integral as computing a transition amplitude. You have some asymptotic.
I would call that an inner product.
No, because the inner product has to be defined in the multiverse Hilbert space. Okay, just to be very precise, if you have a notion of asymptotics. I won't hold it back. But see, if you have a good notion of asymptotic states, you can ask the question, suppose I start with some states in the far past, what will it become in the far future? Okay,
Yeah.
that's one notion of a transition amplitude.
Yeah.
Okay, and the notion of an inner product usually is you have some set of states, okay, and you want to have a pairing between them, whatever, to get some numbers out,
Yeah.
right?
Without any time.
Without any time evolution.
But time evolution is pure gauge here anyway. It doesn't make any difference.
It's not pure gauge because you're starting with a bunch of disconnected universes.
Yes.
And you're asking in the process, and there is, when you quantize it canonically, there is a notion of time, a physical notion of time. And you can say, okay, you start with large universes in the far past, which are evolving. Then you can make that precise. And then you want to ask, okay, what happened?
Sure, we can call this a transition amplitude if you like. It's the same thing. Like it's just we're starting with these asymptotic states in the Euclidean past and looking at their overlap with the Euclidean future.
Yeah.
There's Euclidean time evolution in middle, right? So we can call it a transition amplitude.
Okay,
I was just calling it.
I'm just saying there might have been some path integral rules, I don't know, which would have just given the cylinder transition amplitude. I don't know how to define that path integral.
No, that I think is pretty well defined. Like that is, it's just like doing standard canonical quantization. For example, in JT gravity, there's a classical phase space you can construct. And just quantizing that naively will give you this sort of product.
No, there's a much more richer story there, allow me to say, because if you could do that, it's a different quantization which doesn't agree with the number of states you get.
That's right. This is more like Sachin.
Yeah,
that's like
and you have that alternate quantization.
Yeah.
But you have a different number of states there compared to what you see.
Yeah, that's right. I agree with that. Yeah, I'm just saying there are two different ways of quantizing.
That's part of what.
And this is like Sachin's standard, and that's like
That's correct. That's correct.
If this is interpreted as an inner product matrix,
Yeah.
the rank of the inner product matrix would be different from what you see as asymptotic states. Because there will be so many
yes, absolutely.
And that is what will cut down, not here, but in this picture.
Yeah, in this picture.
In that picture. So what is the Hilbert space? This answer to this question depends on what the inner product is, right? Because you don't want to remove the null, you want to remove the null states.
That's right.
But Hilbert space in the multiverse or in the single universe?
No, this is all the multiverse. It's all the multiverse.
So this is all, you can put any circle in.
Hilbert space of the full set of closure.
I don't understand this. I want to
It's the same as
transition amplitudes and inner products. What is the structure of the Hilbert space for the multiverse? What are states in the multiverse in a precise way?
You start with just general these
Are
states
they
of
asymptotic
states.
But then I would say each state, each universe can be in an infinite number of different states. Each universe can be in an infinite number of different states. Now you take n of them, you symmetrize, you're going to get some infinity to the power.
So with a string version,
Yeah, that's right.
string
But
version, you can have any excitation there, any excitation here, any excitation here.
Yeah.
But now you think of this as the inner product, and then you will cut down the total number of states that propagate in the transaction.
Many of them will end up being
quotient by the null states.
But in string theory, this would not be the inner product, right? This would be an S matrix.
It's an S matrix. That's what I'm trying to say. If you think of it as a,
we can call it a transition amplitude.
Yeah.
When a transition amplitude is an product between in and out states, like
In and out.
counting number of states, you want the inner product, not an S matrix. So it's important to make the difference.
I think it's just a fair analogy.
You have to understand what the Hilbert space is, right?
Yeah, maybe what you're trying to distinguish is like, for example, in Dissitor, you could have worked at the asymptotic future or asymptotic past, and you want to take inner products between stuff that are both at the asymptotic future. Is that what you're trying to say?
Yeah,
okay, we
yeah,
know that as well. People define it similarly. Yeah, it's all the Euclidean past anyway.
It's Lorentzian past.
No, this is
Lorentzian the problem I'm doing.
That's right.
You're in Lorentzian
You could do
past.
that, but you could also do the other thing where it's in the Lorentzian future and then allow it to come back in time, do whatever it wants to, and then go back. Like it's an in sort of.
See, in string theory, we know what the correct inner product is in Fock space.
Yes.
It's just free particle inner product.
That is what we have been doing, but shouldn't this? If you kind of, I don't know how to define the inner product.
But if we're very far, if all particles are very far away, it's free.
Then
so it's the free field theory,
okay. That is,
So and that's what we want, right? Very early on.
Yeah.
I don't think we should accept corrections to that.
Yeah.
That would be physically wrong.
Yeah.
So we should do something that changes that.
Yes, right. But that's sort of the inner product that comes from the world. In some sense, the world line picture, right, or the world shape picture. There's also the the effect of interactions. These effects are like sort of interaction effects from string theory.
But interactions are not changing the inner product. There is an early Hilbert space where everything's very far from everything. Inner product is not affected by it. Interactions are generating nicely.
Yeah, but that everything being very far from everything else, that cannot quite stay here, right?
You can asymptotically, there is, I claim there's a very good notion of asymptotic states in, say, JT gravity. You know, in JT gravity, if you look at the path integral, you start from DS2 with Lorentzian signature, then you can define a path integral either going via minus AdS2 is the most precise version, and then connect to again asymptotic states, each of which is a de Sitter, in a very precise sense. And then I would say the asymptotic states are like free states, they map one-to-one with what you would get if you appropriately canonically quantize and to the SSS matrix.
So what I thought in string theory the asymptotic the notion came from this target space, the fact that they are far away.
Yeah, you don't need that notion, but you still have a notion of asymptotic single universe states, very far.
So that's kind of, this canonical quantization.
Yeah. I'm just saying you can put together because if you're going to talk about states, you have to have a canonical quantization picture, right? Otherwise, what do you mean by states?
No, right. We can just define some inner product.
You have to say what the inner
We
product.
define some set of states and then
They cannot okay, but you need a notion of a Hilbert space.
Yeah, this is defining both those states.
I'm just saying, if you do canonical quantization,
Yeah.
there is an inner product.
Yes, that's right.
And there's a very precise notion of asymptotic states, which
That's right.
to say the usual states that is canonical quantization.
Yes.
And what about the multi-annual state in the number of states is to 1 by 1, right? 1 by 1.
I did not do a third quantization of the theory, so I don't know how to define a multiverse in a product.
I think that is what he is trying to do. So
This is a multiverse.
But I would just say that, okay, you must go on, I'm sorry, but I would say, in my view, he's computing a transition amplitude.
Why? You're just distinguishing this past future thing. Like this is not Euclidean. Forget about de Sitter for now. Let's talk about AdS. Then this is all just in the Euclidean section. Like this is what you call an inner product. Like thermofield double. Like you have Euclidean past, Euclidean future. You glue them together. That's an inner product. It's the same as that.
in string theory, you would have said it's transition amplitude because these guys were in the very far away.
Lorentzian past and Lorentzian future.
And those guys were very far away in the future. But without having that kind of more physical picture, I don't know why this could not be thought of as a product. This could also be possible.
Yeah.
I don't know. So, what in the AdS case, you finally have some states, right?
Yes.
These states are defined. So, let's say we do AdS JT gravity.
Yes.
Okay. So, you can have JT gravity with multiple boundaries in Lorentzian space.
Yes.
Say 2 boundaries or so on. You can construct that out of some path integral through Euclidean space. And you want to define an inner product of a multi-boundary Lorentzian system like that.
Yes.
And your notion is to take the bras and gets which are created like that and
Do the path.
and do the pathing.
Okay. So
That's it.
So we're just defining this as an inner product. So we're setting up these boundary conditions and doing the path integral. So roughly speaking, this is so I'm just going to define this notation to So these brackets here really mean doing the path integral. Okay, so let's not give it any other interpretation for now. These brackets are just defining doing the path integral with these boundary conditions. And these star here basically mean doing CPT conjugate. So we start from, so these ones in the Euclidean path stay as they are, and there's some CPT conjugation we're applying to talk about the future ones.
And just to understand everything, so we could just do everything Euclidean and the boundary conditions are also all in Euclidean configurations.
Yeah.
So just one back to this question. So why is it that there are no coupling dependent.
Yeah, I would have also expected that it gets modified by things like
There'll
this.
be corrections to be in the product.
I feel like it's an order of limits sort of statement.
For past asymptotic states?
Yeah. Yes.
Why?
Because it's trivial. Everything is very far.
No, but
Yeah, I feel like it's a little, I mean,
Meaning, you may be able to, as Ulkar was saying, you may be able to do a basis change if you want to make it look complicated. But there will be one inner product. Like in field theory, there is one inner product that is very clear. Right? So inner product that comes from the creation operators of the free particle states. That inner product is not in question. Right? We put it inside, Lehmann representation and so on. Right? I mean, it's.
we know that the stream codes are not quite stable, right?
We know. The same
So
case.
then, I mean, if you just work with that, then you would be concluding that stream modes are good asymptotic states, right? But if you these interactions destroy them, even though they are very far away, so they are not. So that should come out of. It would be nice if it comes out of any other product.
You're saying that the decays. We're not the decays. That
there can be some states.
This is the product may take care of that, right? It will tell you that you should not put that if you have interactions.
right. That,
Yeah.
Because you cannot separate the decay. The decay can be made far away.
Exactly.
Exactly.
If you didn't have any
That's
interactions
what-
like the picture we were drawing here, then you would have exactly what you said, because their like number of universes is a good quantum number, for example. But if you have interactions, it can be like wherever you like, there it's. Yeah.
But let me just say, at least in the context of JT gravity, all the interactions are correctly computed by the SSS matrix model.
This is exactly the same as the
Which
SSS.
gives you the I would say, for the de Sitter problem, gives a transition amplitude for some number of universes of some lengths to go to some other number of universes with some lengths. Okay. From that, you can convolve that amplitude, that's like in the length basis, to compute the transition for a universe which you can specify in terms of, other data. Because, saying that the universe has some given length, okay, is not a gauge invariant state in the theory. So you can convolve it to create gauge invariant theories and get the same kind of transition amplitudes. But the separation between defining precise states and interactions is quite clear, because all the interactions are computed through the traces of the matrix model, in a very precise way. Okay, anyway, we can talk about it.
Okay, so good. So there's one important requirement that we put on this on this inner product, or it could be an inner product, which is to require reflection positivity. So we've defined a path integral this way, but it's not guaranteed that it will satisfy reflection positivity. That is, that if you take the norm, so you can define a norm here. Right? So we've defined states using these boundary conditions. So we can look at general states that are sums over I, Ci, Z of J1, Z of Jn.
Just one comment here. So isn't, I mean, I have not studied this much. Isn't this a Paddy-Pulish business of defining correct asymptotic states and attempt to make them eigenstates of interaction happen to you?
Yes.
So in that sense, you are using the proper norm, right? So, with the interactions, allowing for decay.
Would the early time Hilbert space for string theory would just be the Fock space of all stable particles.
Right.
Okay, that would be the graviton Fock space. And that would just be what it is.
Yeah, it may be that if you use this norm, your rank may reduce to that of the graviton pocket.
Okay, maybe.
Okay. Right. Yeah, so it sensitively depends on the choice of, on the path integral itself. So good. So this is the set of states we're considering. We're taking general products of these C's, taking an arbitrary superposition over them. And then in order for this to be really an inner product, we're requiring it to be reflection positive.
What is Z of G?
These boundary conditions.
I'm
I'm just calling it C because later it'll get related to partition functions, but we just think of it as this boundary.
And J is what?
Some source. So like, for example, in JT gravity, it's the length of the circle, or in higher dimensions, you can have some source.
So in JT, this will just be the asymptotic length over phi or whatever, that gauge invariant specification.
Good. So now this is
What did you say about reflection possibility? That this
we require this to, like, in order for this to define a valid Hilbert space, we need this to be a sensible inner product and for it to be reflection positive. Otherwise, it won't make sense. So let's say it's an assumption here that the gravitational path integral as we chose it is reflection positive.
Can you write down the statement of reflection positivity that Z star J1 J1 star J2 star dot 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 is and J1 is equal to
Positive. Yeah. So psi is defined this way, and then psi goes.
Okay.
Okay.
There is no ordering here.
Well, yeah, that's a good point. So here, the ordering of these operators doesn't really matter. There's no sensible time here. So we can just insert this before this and vice versa. That doesn't make any difference. So these are really all commuting operators. So Z of J's, all the Z of J's commute with each other.
You probably want to symmetrize them, right? If you give some kind of definition finally, as in all the universes are on the same footing.
Yeah, so in the bulk that's going to be the case, but like here, there's really no difference. But I mean, they're automatically symmetric. We're just labeling them with some sources.
Yeah. But you probably make them commute, right?
Yeah, they all commute.
Yeah.
All the Z of J's commute. Good. So now we have some set of states, and we've defined the inner product. So and it's reflection positive. So many of these states will have a positive norm. Some of them may have zero norm. And so these are what are going to be called null states. So if psi ends up being zero, then this is the null state. And this is the existence of such null states is kind of standard in gauge theories. In gauge theories, anything that is pure gauge is sort of not a real degree of freedom. And so so you have a pre-Hilbert space. So there's a set of states that we defined here. This you can think of as the pre-Hilbert space or the kinematic Hilbert space, which is just the set of configurations we're considering to start with. And then after we have these, after we compute the inner product, we find these set of null states labeled by n. And then the final Hilbert space will be defined by this kinematic Hilbert space quotiented by the null state. So basically, we're removing all the null states, and now we're left with a Hilbert space that is well defined in the sense it has positive norms, like positive definite, not positive semi-definite.
At least in usual gauge theories, the kinematic Hilbert space is bigger in a sense because you still impose the constraint.
That's right. So here
your claim is that you have some gauge constraints here.
So that's a good question. So here we defined all of these by asymptotic boundary conditions. So in that sense, they were already gauge invariant in the naive sense. What's ending up happening here is some more non-perturbative version of gauge invariance. So it's not clear what that really means, but it's cutting down the number of states even more than you would have otherwise in perturbative quantization. Some states which you naively thought would pull different actually end up being similar. That's the same.
States in the multiverse, what are these states and what precise canonically quantized theory are these states in? Because the single universe states are all gauge invariant and infinite in number. They meet all the constraints.
They're not all independent though.
I mean, what I'm trying to say is, you can take the single Hilbert space and impose all the gauge constraints and ask how many states you have. There's a
you mean perturbatively?
Non-perturbatively in the single universe sector, okay, and you map it.
I would call that perturbatively. So here we're very.
Well, I don't know
what in canonical quantization.
It's an exact quantization. You have a choice corresponding to the two kinds, the cylinder.
I mean, ignoring topology change.
No. With topology change. The single, Gordon says the single universe Hilbert space maps in a very precise sense to eigenstates of the matrix. The matrix model has topology change. That topology change you don't compute in canonical quantization, but you have a notion of asymptotic states that you can compute in canonical quantization and map to the matrix.
I'm a little surprised by what you say because, so for example, in AdS JT, the canonical quantization is much smaller than the set of matrices. Like it's very different from the set of matrices. It doesn't see the SSS matrix. It's just a two-dimensional phase space that Harlow and Jeffers defined.
Yes.
There's no relation to the matrix at all at that level. You only see the relation to the matrix when you do the full path integral, including topology change, etc. So there, I would say the canonical quantization phase space is just different. There is a sense in which is gauge invariant. It's the standard imposition of gauge constraints. And you get some Hilbert space from that. That's very different from the SSS Hilbert space.
In De Sitter, there's a 1-to-1.
Okay.
Sure. Well, let's talk about it later. Okay.
Very good. So So what we've done here is now remove those null states, and then we've defined a dynamical Hilbert space. A dynamical Hilbert space where now everything is a meaningful state. There's no null states, and each of these is a physical
I
state.
should not think of this Hilbert space as the Hilbert space of closed universe, right? It's like the third quantization.
Yeah, so you would call it the Hilbert space of closed universes, but it's the Hilbert space of closed universes. Yeah, right.
Implicitly, you're doing third quantization. But
This is third quantization. This is
But I
third
mean,
quantization.
if one wanted to do it, one should just try to do honest to goodness. Boggles my mind, but do honest to goodness third quantization. Take JT theory in Decider and do honest to goodness third quantization.
What is honest to goodness? Like,
Honest
what is
to
not good about
You
this?
construct a theory which has a Lagrangian or Hamiltonian, let's say a Hamiltonian layer operators
Yeah.
which create universes
Yeah.
and interactions in that theory.
Yeah.
And then you try to quantize it, and there's a notion of self-adjointness in that theory and,
Right.
and all of that, right?
Right.
And
Yeah.
it's a messy business.
That's
It boggles my mind.
Yeah, that's true.
Okay.
Yeah, I mean, it hasn't been rephrased in the language that you want.
That would be string field theory for wedge shapes.
Exactly.
That would be the analog.
Yeah, that's right.
Exactly.
So it is complicated.
Okay.
So here we're just defining it using the path integral. Okay, good. Fine. Oh, just another thing. So here we had all of these states that were defined by the set of boundaries. It's convenient to define an operator. So we define this operator Z hat of J, which basically acting on some number of boundaries, just adds an extra boundary. You just add in the boundary Z of J1 with the other boundaries that are already there.
So it's like a creation.
So this is like a creation, and in fact, I mean, it's really like a creation plus annihilation operator, because this can, if you add this in, so imagine you had this configuration and you added in one of these things, it can absorb a universe or create another universe.
So, what have you added in here?
Just an extra boundary. Basically here I'll just add an extra boundary.
Okay.
Then so this is just the operator that's defined.
So why are you not calling it creation?
Because
I mean, state it is creating, right? I mean, why is it why was it absorbing?
Is it that it can get rid of one of the
here's a simple example.
Now, past and future, but acting on the state should
We
be
are
a
talking about
creation.
state giving a new state.
Yeah.
So here's what we started with, let's say.
Yeah,
And there was some universe.
That was fast.
Yeah.
This was
It's a
this.
creation.
And then we add Z of J. It can add another universe. Something like that. I can add a universe. But there's also that diagram, which would delete a universe.
So it's like a phi operator which has A plus A.
It's A plus A diagram.
I see, but I thought that this, when you do the cat, I thought you were writing just the, this is not like far past. I was thinking you're just starting with whatever, 2 to the n, 2, 3 all the way to the n initially, and you're now having one more boundary.
That's right. That's what we did here. So let's say we had 1 and 2. So 2 and 3 or whatever. J2 and J3.
Yeah.
And now I added J1.
J1.
And I'm just saying it could have done both actions. It could, I mean, it could. So let's say when we had J2 and J3, we had something like a cylinder which had one universe.
Okay.
But now when we've added this J1, there's a possibility of this, say, getting absorbed here and that one just being disconnected. So that in the middle, there's 0 universes. So that's like a deletion. And on the other hand, it could have also created a universe because it could have done something like a pair of pants.
So this symbol here denotes the whole path integral.
Yeah.
Not
No, this is the state, right? Like, so it's the whole
Just
state.
as a state, it's just adding a circle.
As a state, it just adds a circle. As a state, it just adds a
Then
circle.
you evolve it. I
Yeah.
thought the thing is, so you specify the state, say the cat, the bra, and then the gluing rule is that you connect every which way. So in the gluing rule, you might, in a sense, pure deletion, right? Like,
Yeah, I mean,
that's the way.
there is not that much of a distinction between stuff that's in the Euclidean past and future. The only thing is the star, right? So this inner product is computed by this path integral, and everything here commutes. You might as well put things in the Euclidean past, or it's just a question of the star. So it's not so clear it's creation or
Be counting all boundaries together.
yeah, it's really all boundaries that they have.
So
You can normal order these also.
Okay, then I
Uh,
guess guess it's a Euclidean word.
You don't want to contract these things.
You could, I mean, that's not what automatically happens in the path integral. You could try to do like subtract or one point functions, etc.
Where you all the correct correlation functions.
Yeah, you could do that.
So only those ones are to be of just combinatorial.
Yeah. There's a very similar factor.
Yeah.
The type of null states that you have for
That's
the
Yeah.
that's what happens in the general case when you canonically quantify. You have a notion of universes. Universe is contracting or expanding.
The number of null
depending
states
on how the momentum quantity.
The null states are for the whole Hilbert space. So the whole Hilbert space is like for arbitrary number of universes.
Start with
Right. So we're starting with all possible states of this type for arbitrary n.
transition.
We're not fixing the number of universes.
Okay, so
We take that
full 1 to infinity.
Yeah, from 1 to infinity, and we have like all possible such configurations. Look at all of their superpositions, and then find the null state. So the null states is defined by that full set, and generically it could be like some different number of universes combined to be a null state. It could combine different number of universes. There's nothing.
And no matter how they combine.
No, I mean no. The way in which they combine will depend sensitively on the path integral. The existence of such null states will be very sensitively dependent on what the path integral is. Right? Like, yeah.
To join
It depends on what the inner product is, right? So you just do that path integral, you see inner product, and you see whether it's zero or not. And then you find, in examples, you find that there are different models where you do find such a large transition.
Maybe a plus minus.
So does these universes have something special which are giving you the state?
No, not really. I mean, it's kind of open. What ends up happening is some crazy combination of universes ends up being null. And there isn't some obvious way to see why that particular combination will be null or anything like that. So, yeah. So, like for example, there's a very simple model which is even dumber than basic gravity, which is just the topological model, where the inner product is just defined by summing over geometries like this, and the only action is just like the Euler characters. So, like all you count is the topological. And there, what ends up happening is like the partition function ends up being something like an integer. So, one example of a state that is null is something like sine pi z. Because if it's an integer, then every such term will vary. But that's like an infinite sum over arbitrary number of universes with some specific coefficients and so on. So it really depends on the theory what this null state will be like. It's very sensitive to that. Yeah, so it's very hard to say what they're going to look like, but they exist, and we can in models we can see what they are.
The dimension of this space after quotient is given finite.
Not always. So, for example, in the Marolf-Maxfield model, which is a topological model, it ends up being countably infinite. It's basically discrete. It's all the integers. Like the spectrum will end up being all the integers. And in GT gravity, it's uncountably infinite because it's labeled by basically all the elements of the matrix model. Like each different matrix is one state. Yeah.
And so this and there is this I mean there's two triangles.
So sorry.
Some non-compact is what gives gravity.
Yeah, I know. This is the fun.
But I think it might be more similar to the topological model. Like it's just weighted by the Euler characteristic. I think.
Yeah.
And then I think it's the same as the Marolf-Maxfield model. Yeah.
Model is what?
It's just that, like the action is just chi, like e to the s not chi. That's Euler characteristic.
So what is the, so up till here I was sort of with you, what is the Marolf-Maxfield?
I was just giving an example. The question was what null states are like, and I was just saying that when you do this process, you'll end up finding some null states. I was just giving the example that in Marolf-Maxfield, one of the examples of what a null state is this state sine pi z. The spectrum ends up being integer, and so if you just expand that out, that's like some crazy superposition over many different number of universes, etc. That just happens to be null. If you use the inner product given by the path integral, you find that's null. So it's a very sensitive thing to the gravitational path integral, what it is that is a null state. Yeah.
So I got confused when you put that state.
Yeah.
I thought the state was specified by specifying boundary conditions on it.
Yeah.
So what is sine pi z?
So imagine this is some fixed j. Okay. We can expand this.
Sine pi z of j.
Multiple inputs, say operator.
Maybe instead of saying this, let me just complete the discussion of the operator. So then I get back to that. So
just to understand the statement is that in the multiverse Hilbert space,
yes.
You might have thought that you have, even if you have two states for any one universe or something, in the multiverse, as you include the number of universes,
Some combination of them
you get 2 to the n states, but actually there's a cut down in the multiverse.
That's right. Yeah, that's right. So this Z hat, so all of these states that we define, we can now define a sort of vacuum. Okay, go ahead.
Yeah, just a small question. So I was confused, like usually when we compute inner products using Euclidean path integral, there is a slice on which they scale.
That's right.
So here there is
no, it's because of different variance, roughly speaking. So if you were just doing canonical quantization itself, then in this case, there's a gauge constraint relating them, right? So H is just 0, there's no boundary. So whether I compute things on this slice or this slice, it's gauge invariant, like it's diff invariant.
Okay.
So it doesn't matter. There's no real time evolution in this case. In this path integral, it's a souped up version of that. Basically, I can compute it on any cut. The definition of the inner product was just using what the asymptotic boundaries were. You held that fixed, then it doesn't matter where you're trying to interpret this as a cut. This is just defining the inner product, and it's for all of those slices.
So Pratik, the null space constraint that you get from this inner product, and also this identification that you get from where you cut this cobordism.
Yeah.
Are they kind of the same?
It's not being made very sharp. Like this cobordism thing hasn't been made very sharp. Like people talk of it as
things.
Yeah.
Here you see one cycle, here you will see two.
Right.
And with different dimensions.
Right.
And all
Right.
so
Right.
This is must be equal to this.
It should be the same.
And does that come out of this inner product matrix?
I mean, yeah, if you do this calculation in any model that you like, that is the thing. I don't think it has been made like in full generality, it hasn't been discussed how to talk about it in that language. People use the word non-perturbative gauge invariance to mean that fact. But I don't think it has been made super sharp. Like it's only at this level.
But the states are finite and that cut I can make any slice.
So there is so firstly, already in gravity perturbatively, there is a huge gauge constraint, right? Like because whether I talk about, as you were saying, like different, there's a constraints that are relating all of these slices and so on. So there's already a huge constraint at that level. I'm already assuming that. So forget about that part. Then there's also these topology changing processes, etc. And like that's some more non-perturbative version of it, which you have to account for. Then that cuts down the states even further. So if you did canonical quantization, for example, JT gravity has a different phase space. And then when you do this thing, then it has a different Hilbert space.
Abhijit, I don't think it will be exactly what you're saying. Because in string theory, you can have two gravitons scattered to two gravitons. It's scattered to each other, but they are in the same state.
Yeah. Yeah.
I think it's what you earlier said, that the decay somehow, that imaginary part is it.
So the Euclidean thing is important.
Sorry.
Yeah.
This Hilbert space each after the cut down of null states.
Yes.
How is that related to the matrix for the Hilbert space?
So I'll just get to that. So I'm almost there.
Sure.
So
It's supposed to be related.
Yeah.
A single universe is not me.
No, I'll answer.
So one feeling is that it is so abstract that the entirety of the theory has become an inner product. What are the observable things? Are there operators on this quotient?
It's at the same level as you would do in AdS CFT. In AdS CFT, the only observables are like boundary sources.
No, but what are they? So what are the observables? I mean, it seems that everything is in the formalism of inner product. So what are the operators or what?
So for example, in JT gravity, this is some like the observables you can define will be some functions of these things, right? So you have different Z of betas, you can have many of them and so on. And you can interpret this overlap as some, like, for example, Z hat of J, that's an operator, right, in this theory. That's like a discretion plus annihilation operator. So basically addition of extra sources. That's the sort of thing you'll find. It'll look more like the standard sort of rules we use in AdS when we talk about situations where we cut through an asymptotic boundary. There it will look exactly like that. But this is in the situation where it's just you're cutting through this finite universe, and there all we're doing is adding or deleting extra sources because that's all the states we have. Yeah. So
suppose I have a two.
Yeah.
So there's a pair of pants and
Yes.
this, let's say.
So let me just draw what you're saying.
And a pair of pants. So now if I cut this open in the
Two cylinders. And another pair of pants?
Yeah, because I have to do the full path integral, both these topology will be.
This plus the pair of
Oh, this plus
Yes.
pair of pants. So one of them is disconnected. Oh, you want like that? Double pants.
Oh, yeah.
Four pieces. Yeah.
So this is,
Yes.
so these two will contribute.
That's right.
Yeah. So
That's
if
right.
I have cut open this,
That's
equity, then there is a possibility that I get 4 closed universes.
Two or one. Yeah.
2 plus 1 or 2 plus. I get a linear combination in general, right? The state of the region.
Yeah, you're saying that this term is interpreted as a two universe state and this one is as a one universe state. That's right.
Yes, but when I cut it open, it is possible that I get linear combinations.
That's right. So I think what you're saying, if I can just try to say that, is if I cut it here,
Yes.
then there's one universe.
Yes.
If I cut it here, there's two universes.
Yes.
But there should be some gauge invariance relating
And
them.
so the difference between them is supposed to be a null state.
Yeah. So basically it's saying that this two universe state and that one universe state are secretly the same thing. They're related by some constraint.
So whenever there is disconnection, there will be null states. Because the figure that you drew earlier.
Yeah.
Then we can just have it in between this weird.
No, but then I want to distinguish null state from that empty state. So I'll just talk about that. That's different.
But you must but I mean, the same thing is that, when you have these Euclidean path integrals, they are computing tunneling amplitude. So we have some notion of asymptotic states in Lorentzian de Sitter. And, you go through whatever configuration you.
I mean, in AdS CFT, this is standard, right? Like we always compute these Euclidean path integrals and that evaluates an inner product.
No, but if you're going to associate states when you cut it,
Yes.
then, at least normally you can have Euclidean configurations describing instantons, but states correspond to, not intermediate configurations in the path integral, right? They correspond, especially if you're changing signatures, right? So, is there any precise sense in which if you've got some Euclidean configuration and you're cutting it, you've got a state?
I don't know. I mean, like, what would you say about the thermofield double? Like, there we have some Euclidean paths which create some state. We cut it open here.
You cut it open and you continue because it's a movement of time symmetry.
But this thing is computing the inner product between these two.
You cut it in the middle at a rather specific location at a moment of time symmetry, and you connect to a Lorentzian configuration.
I don't have to specify this as an inner product.
I think as a mathematical statement, it does define a vector space. So it's not a substrate, it does define a vector space, right? This inner, if you take this as inner product, it defines vector space. Now, I mean, maybe the question can be about physical interpretation. I will not sure. So what would be the physical question?
I mean, if you, at least the way I would say it is that till you haven't cut it open at a moment of time symmetry, it hasn't become a state of two disconnected boundaries in a Lorentzian sense, right?
I mean, it's a state, like in a CFT, we can compute inner products between CFT states using a Euclidean path integral. Like, would you say that is a inner product or no?
No, I think
Okay,
what maybe
then
perhaps Sandeep is saying that if you cut it there,
Yeah.
the derivatives across are not vanishing. So you cannot continue evolving it in Lorentzian space.
That could be, but that's not important for defining it as an inner product.
No, I mean, I
Like
guess
in
you
a
want the
CFT,
Lorentzian state. You want the state in the Lorentzian geometry.
Would you say the same for CFT? Like in a CFT, I can cut open a Euclidean path integral and I would call that a state.
It's only because
Even before I analytically
often
configure
what
this.
happens in CFTs is that there is a inbuilt analytic continuation. We are not always
We
very
need not have a time symmetry on the path integral. Like we can construct like some crazy path integral which doesn't have time symmetry, cut it at some point. No, that's the inner product between two different states prepared by two different path integrals.
Yeah, what I mean is, in 2D, you must go on, but in 2D CFTs, if you take a sphere and you insert an operator and you center and so on with a conformal map, you can take that to be a cylinder we are inserting in the far past, and that cylinder is actually can be easily continued to Lorentzian space.
Yeah, but I don't
This
think
is
that's
just
important. Like we could have an arbitrary geometry, like some arbitrary Riemann surface. We have something with some genus, etc. And we cut it open on some surface here.
Yeah.
That will define some state.
No, but there is a mechanism, right? There is a state operator map is crucial.
Yeah, there is a mechanism.
That's crucial. This is true in any quantum field theory.
Yeah, any QFT. In this example, you could have cut it not at k equals 0.
Yeah, I can cut it on any non-time reflections. I don't see why that's important.
There's a Marolf-Maxfield wave function for JT gravity on that at k equals 0.5. And it's the overlap between those two things.
Say again. You cut
You
it.
cut it at not
I think what Omkar is saying is like here you could have not cut it here and instead cut it on some surface like that.
Yeah.
Something like that.
There's a state.
There's a state here, there's a state here, you take the overlap reflections.
There's an inner product.
No, there's a well-defined state in the Lorentzian theory for that cut.
It's just that a different value of k, right? Usually we are used to setting k equals 0. Set k to whatever. Some other.
So, is it possible to give an example of a pair of orthogonal states?
Orthogonal states? It's actually hard. I mean, they look complicated.
I want to see all these connections cancelling and giving.
Yeah, it is really hard. Like it's very complicated. I mean, the simplest example we have of that.
This geometric progression.
Yeah. All such nice. I'll tell you what happens in the simplest model. Like, so let me just complete what I was saying. Yeah, Marolf-Maxfield is basically the only one where we know how this works concretely. Yeah. Good. So, okay. So we defined all of these states. Now, since we've defined this operator, you can just think of any of these states which contain n number of boundaries as just being constructed by these Z hat operators, acting on what you can think of as the vacuum. The vacuum is like the empty state where there's no boundaries at all. So that's related to your question. So that's what we call the Hartle-Hawking vacuum. The Hartle-Hawking state is like the empty state where there's no insertions of any operators to its past.
Because you created everything.
Yeah, it's basically the no boundary. So and then this thing is just the state. So that's just how we're defining the vacuum. Now, so we're almost there now. So now we have everything that we need. The important thing that we noticed was that Z hat of J1 commutes with Z hat of J2 for all J. Right? So for any choice of J, these things are simultaneously diagonalizable. And so essentially what you can label the Hilbert space by.
Confused me. So I was thinking the Hartle-Hawking state is of course a state you created out of nothing. But then you're saying that acting on this operator, you get a single, if I'm right, single one boundary state. So there's a sense in which you take the Hartle-Hawking state, you act with this operator, and you get another single one boundary state.
So imagine something here. This is the Hartle-Hawking state, but there was nothing. Then on that, we act with this single creation operator, which takes us here. And this thing is, it's single boundary in the sense of single asymptotic boundary that's been inserted.
Yeah.
That can lead to a state which has multiple universals and so on. That's all.
Later,
But it's a single asymptotic boundary.
Single asymptotic.
String creation operator.
String creation. Yeah. Good. So since these are all simultaneously diagonalizable, we can label all the states using the eigenstates of these operators. So essentially what we're going to define is what I've called these alpha states. So that Z hat of J has an eigenvalue that's called Z alpha of J acting on alpha. So these alphas for different values of Z alpha will end up being orthogonal. So the different alphas will be labeled by all of these values. So they have to be eigenstates of this Z operator. That's what makes it so complicated, because it feels like you've created an operator, but still this thing should be the same up to a number.
That's the sign kind of thing.
So the sign kind of thing is like null. So there it's like not even that. But it has to be something where there were already a lot of stuff floating around. And this is a new thing. String coherent state. You can call it a string coherent state. Yeah, it's a coherent state.
Exponentiated.
It's exactly a coherent. So, yeah, if you think of this as X, then it's like right. Or A as A, I guess A.
Okay, so now that's the alpha state.
Yeah, so that's the alpha state. Okay. So we're labeling all of this full Hilbert space, and right now we've not talked about any particular theory. There are theories like this Marolf-Maxfield theory where we can actually work out what these alpha states are, and even there they look complicated. Like what
is the number? that a number?
This is a number. So this is an operator. This is the operator we defined there. This is the state, and then this is the eigenvalue corresponding.
So just a couple of clarifications. J is the various states on one universe, right? Or one string.
Yes, like say the size
Various
of the
operators.
universe, or yeah.
In
Oh
string
yeah,
theory,
in string theory,
the various
it's called it, yeah, various operators.
Okay. And just to make sure, everything that you say here should apply to string theory. Is this right or not?
I am a little confused about that because of this point about transition amplitudes versus inner products, but modulo that point, yes.
Yeah.
It's very similar to that, yes.
But I mean, if I want to test it, I'm a skeptic, I should be able to implement it in string theory. And just see what it gives. Because that's a very clear example of 2D gravity.
Yeah, I think so.
Okay.
Yeah.
And not to discuss this now, but one thing that's important about string theory is that the on-shell condition is two solutions. There's P0 is positive and P0 is negative. Because P0 squared is something and that's plus minus, and that helps us with out states and in states.
Okay.
And I was wondering if that is going to play a role.
By the way, we were having this side discussion. That's exactly what happens in JT.
Yeah, that's related to this point about transition amplitude.
And that's why it's a natural thing to think of these as transition.
Yeah. So I'm not sure about that specific point because the usual situation where these things have been like explicitly constructed and so on is like in AdS where it's like it doesn't really matter so much that it's Euclidean future or past. When we introduce something like de Sitter, I guess that's a point to think of.
Yeah. So actually, this map I was saying is in fact when I was saying you have these states in the past, they are corresponding to one sign, contracting universes. So and then you work out the transition to the experiment. So
I'll just say a few things about that. Okay. So this is how we're defining these alpha states, and then any of these two alpha states with different alpha will end up being orthogonal.
And just to say, if these Zs would just be the vertex operators of string theory.
Zs would just be the
each vertex operator creates
these.
Just vertex operators.
No. It's creating a string.
So does a vertex.
So it's a vertex operator.
No, vertex operator. Okay. Sorry.
Right. So and this thing is a complete specification because the set of states that we considered was basically these kind of states, Z of K1 versus Z of Jn. And then we can take the overlap of this with alpha to see what it is. And this is just, we can just think about all of these as just operators acting on this. So this will just become Z alpha of J1 star. This is the alpha of Kn star. So we've all separated the action of each of these and then pulled out the Hartle-Hawking state. So the empty state is the Hartle-Hawking state. We take the overlap with alpha.
So basically, you've summed up all the multi-universe states in some combination carefully. So that now you don't have to worry about creation of extra universes.
Pratik.
Yes.
Alpha state, does it have one more time asymptotic boundary when it is acted by
No, so just to give you an intuition for what it's like, in Marolf-Maxfield, for example, these alpha states will end up being things that already in the Euclidean past have an infinite number of, it's like a coherent state. So, it already has all of these infinitely many modes excited.
So one more
will not make a difference because it just shifts everything, but there's still infinitely many. That's the idea.
So the alpha state should have a label J, right?
Alpha, it's not one number.
No, but it should depend. That definition is an alpha.
For every J, there's this eigenvalue.
Yeah.
So alpha is the collective set of all Z's of J. All Z of J. So all J's have to specify. If I tell you what the value of Z of J is for every J, that will specify alpha.
So I thought alpha would be something like this. In this
it should be correspond to a state.
Not for fixed J.
That's usually
this state should obey equation of this.
But it should do this for every J.
Is that the moment?
Why
not just for particular?
This is for all J.
For all J.
Why is that?
I mean, I can specify. Like they're all simultaneously diagonalized, to state.
So you just have to.
I guess you can think of it as roughly that. Okay. Okay. Good. So then we can just work with this. So we can think about that overlap as some probability distribution. Okay, so about square. Normalize it in some way. And this is a probability distribution because alpha is now a complete set of states. So alpha is some complete basis for this Hilbert space that we've built up, where in the Hartle-Hawking state, the probability of being in state alpha is given by this probability P alpha.
For the orthogonal?
Yeah, for the orthogonal, because they're different eigenvalues.
But no, I mean, I thought coherent states are not orthogonal to each other.
Sorry.
It's not like a coherent state or something. Because they're saying that it's an eigenstate of X. So it's like a delta, not a coherent.
Okay.
Yeah, I guess if it's like Z as X, then it's like, then it makes a difference that it's an eigenstate of X.
So that coherent state was wrong. Yeah.
Yeah.
So it was Schrodinger function.
In terms of creation operators, it has multiple universes, right?
But you know,
in that sense, yeah,
but he was saying that Z both creates an
yeah.
So it's more like
What was this? Sorry, I missed something.
Eigenstates of X.
Yeah, it's a Hermitian operator. Yeah.
Z is
That is a Hermitian operator. You should think of it more like X. So then this is more like a delta function or plane wave. Yeah.
these states, is it? I see these eigenstates.
And then they're orthogonal.
So, can I ask the original path integral you had, which was the z of j1 to z of jn? I can think of that as now a correlator between Hartle-Hawking states because of the way you've written.
Yes.
that I start with no universe in the past, no universe in the future, and then it's computing some correlator in that, right? And now these alpha states, I'm to think of these alpha states as something that I can insert whenever I cut this path integral, and I'm allowed to insert a complete set of states. I can insert a set of alpha states there.
Yes.
Is that
Yes.
how I'm
Yes.
Okay.
Except that alpha is going to be some very complicated mess. So I mean, it doesn't have a nice picture, but yeah, it's correct to insert it in the middle.
Okay.
Okay, good. So then, as you were saying, like if we compute something like z of j1 or z of jn in just using the path integral, the thing that's being computed is we can insert a complete set of states over alpha, sum over alpha. And then all of these z's are eigenstates of alpha.
But why is this not the degenerate eigenspace?
Could be.
So what do you mean by alpha state?
What do you mean? I mean, what the probability generates?
That equation here. That equation here.
Yeah.
This equation is supposed to define a state.
For all j, yes. If that equation for all j will define one alpha.
And why is it clear that it defines one state? Why is there no?
No, it could be degenerate.
Yeah.
It could be
Okay.
degenerate.
So what's we mean by that? Yeah, but we just someone wants to do some probability distribution, right? That's what I.
I mean, we can use some label for, like, if there are two of them, we can call it alpha 1 and alpha 2. And then we have different probabilities for each of them. Like what? Degeneracy doesn't change any of this. Right?
So you want to kind of orthogonalize?
Yeah, you orthogonalize, like orthonormalize it.
And to just look at the probability distribution given by the eigenvalue.
Yeah. Okay. So now we can insert this complete set of states. So let's say we insert it at the end. Each of these z's has alpha as an eigenvalue, as an eigenstate. And so what you're going to end up with is z and the product of z alphas for each of these. Z alpha of j1 up to z alpha of jn. Okay. And in the end, you're going to be left with something like alpha HH.
Oh, that's the
matrix alpha HH, alpha HH. Okay, so this is basically this thing. It's going to be alpha. As long as we normalize this by Hartle-Hawking. By the Hartle-Hawking norm.
So I didn't understand this. So you're going from that line to that line?
Let me do this a bit more clearly. So this P alpha we just defined this way. Now we're trying to compute basically. Using, so here, remember that angle brackets just mean
We try to compute that I get, yeah.
And then all I'm doing is putting
You just insert it.
yeah, insert a complete set of states. We have a sum over alpha. Zeros.
Okay, I mean, alpha here orthonormal, is it? I missed something.
Yeah, that's what Abhijit was asking us. They're all orthonormal because they're specified by different eigenvalues. So remember that each of these, so these are all z hats. So we can think about this as being prepared by action of z hats on the Hartree-Hawkins state. Then we insert a complete set of states with alpha here. All of these z hats acting on alpha have an eigenvalue z alpha. We have a sum over alpha times z alpha of J1 up to z alpha of Jn times HH alpha alpha HH. So this thing is mod squared, which is basically P alpha times this norm. So if I factor out this norm, this is basically sum over alpha, P alpha, Z alpha of J1, dot V alpha of J. So if we were to compute normalized path integrals where we normalize by this HH, and this is a natural thing to do because this, like in quantum field theory, is all the bubble diagrams. It's like all the things you had without any insertions anyway, like the sphere and so on. So that's the natural thing to compute in a normalized way. Then it's just given by this sum of alpha over this product. So the way to interpret it now is each of these alphas. So now let's go back to thinking about the standard AdS CFT picture. There, each of these z's would have been thought of as a partition function of a CFT, right? It would just compute a number. Now, obviously, here we've seen, suppose there exists a non-trivial set of alphas. Then it's not just a number, it's an operator. And it evaluates to different numbers on different alphas. So the way we want to think about this is each alpha is one where it gives you a definite value of a partition function. So each alpha should be interpreted as a CFT or whatever, one boundary dual thing. And so what we have is, so alpha is the set of theories. So now we're trying to interpret it in AdS CFT. We are averaging or the ensemble.
Some sense in the SSS matrix model, alpha is the choice of alpha.
Yeah, so it's exactly. So the simple example where we understand this. So that's the caveat to some of these things, which is that we understand the path integral well enough in 2D to make claims of that. The two models where we understand it is the Marolf-Maxfield model, where the set of alpha is just labeled by integers. So it's just an integer that labels the size of the dimension of the Hilbert space. And the other example where we understand it to some extent is the JD gravity model, where the dual is an average over a set of matrices with random Hamiltonians. So the alpha is labeled by one choice of Hamiltonians.
I have
Yes.
a very basic question.
Yes,
We were
yes.
talking about the multiple universes where the CFT is living.
So CFT is always living at the asymptotic boundary, right? So normally, so imagine what we would have done in CFT to compute the partition function, right? It would be some path integral over some, so this Z of J is like some boundary with some resources and so on. That's just the CFT partition function we're trying to compute, normally in AdS CFT. And in AdS CFT, we then fill it in with those boundary conditions. So the asymptotic boundary is where the CFT is really living.
At every circle.
At every circle, there's a CFT,
Oh.
and we're trying to compute partition functions. But now the interpretation is, if that was really true, then things would have factorized, right? So we found that Z of J1, Z of J2, at least seemingly, I mean, in 2D models, and even seemingly in higher dimensions, from the gravitational path integral gets contributions which don't factorize. This is not equal to Z of J1 times Z of J2. Right? And that in this language, from this formula, it would have been true if there was only one choice of alpha. Right? If P alpha was just one for one choice of alpha, which is what we usually think in AdS CFT, then it would have been automatically true. But if there are such contributions, then this way of interpreting is to say there exists other alpha. And then we're just averaging over those things. So there's no reason for these to be the same because product of averages is not the same as average of products.
Sorry, I did not quite understand how
Yeah.
you made the jump from alpha being states.
Yeah.
And then to the fact that alpha you are considering as set of theories.
Yeah.
You are averaging.
So far we were talking about the bulk theory, right? So we're talking about the gravitational theory where these things were preparing states. The reason they were preparing states was you added asymptotic boundaries, and when you cut it in the middle, it was preparing some state of a closed universe. Now, in standard AdS CFT, think about what those asymptotic boundary conditions were. They were just computing numbers, right? So, for example, one of the boundary conditions you could have had was just like a circle of length beta. That's like Z of beta of that CFT. Or like in this case, like in 2D, it would be like a Hamiltonian, like a random Hamiltonian. That's just some number, right? So if you have a fixed CFT, that's just a number which is computed up as a path integral, which completely factorizes.
No, but if you have a fixed CFT, you can have different states in the bulk as well. Right?
That's only if you cut through the asymptotic boundary. So I want to distinguish between two things here. So what we normally do in AdS CFT is, let's say we have the thermofield double. We have some asymptotic boundary like that, and we cut it open in the middle and define a state where this state now has some asymptotic boundaries here, right? So thermofield double state is like a cylinder where there's two asymptotic boundaries on that slice. That's different from what we did here, because here what we did was, this is in the Euclidean past, and then we cut it open somewhere here. Right? We're cutting it open away from all asymptotic boundaries. That's not something you would usually consider as anything in AdS CFT, right? All that would happen was this would get filled in with a disk, and you would still have the empty state here. Nothing would change. But when you have these non-factorizing contributions, that doesn't quite happen, right? Because, for example, you could have another cylinder, another thing here, and they can fill in with a cylinder. Then you would have a closed universe in the middle. So what I'm doing is trying to, you can think of this as a souped up AdS CFT dictionary, where we're just thinking of these as creation operators and then cutting it in the middle, not on an asymptotic boundary. And this isn't just cooked up, this is literally what we do in JT gravity. This is how we can compute things in JT gravity. Yeah.
So your full description is extremely general.
Yes.
You could have done it in any direction.
So modulo the fact that the gravitational path integral should be well defined.
Of course.
So the main constraint in thinking about the gravitational path integral in higher dimensions is there's loop divergences, conformal factor problem, etc., which makes it complicated. And that is why people usually didn't consider it. There was initially, of course, all of this excitement from Gibbons, Hawking, etc., that we could compute the black hole entropy and so on. But it was thought of as some effective thing and it wouldn't be a complete description. Here, we're taking the gravitational path integral relatively seriously. And partly the motivation is in 2D, it can be made very precise. In higher dimensions, it's not clear, but it has given us these interesting contributions. And the important fact here was these non-factorizing contributions, right? It could be that maybe we add in other ingredients into the gravitational path integral to make it make sense, like maybe you have to add strings, branes, etc. But if you could come up with a definition of some gravitational path integral which would work with these boundary conditions, then you could run the same formalism. And in string theory, usually you would say there is no alpha left. Everything is just completely fixed. It's completely fixed by the CFT. But here, now we're saying so either it is the case, so there are these non-factorizing contributions. Either it is that those shouldn't be taken seriously. Maybe they cancel with something else and so on. So that secretly everything factorizes. Then that undoes a lot of the progress we made in other things, right? Like computing things using those wormholes. Or it could be that we take those seriously, but then we have to understand what is alpha, like what are we really averaging over? We don't really understand that either. So that's sort of the conflict here. But yeah, the formalism was very general. Yes.
In the case of the string well sheet, is there any sense in which alpha is some state in some boundary theory?
Yeah. Sorry, that was a question.
In the case of the string well sheet, is there any sense in which alpha is some state in some boundary theory?
No.
Alphas are basically the various ones.
No, I don't think so.
No. So it
because
doesn't
it's
seem
not
like
a one-dimensional Hilbert space or something like that, right? Like you have a non-trivial Hilbert space. If you wanted, you could have tried to interpret it in terms of these different alphas, I guess, which would be like a...
For each vertex operator,
One-
there
yeah,
is
like a-
there is a
Yeah, each vertex operator is an alpha. I
Alpha,
guess.
roughly.
Yeah, roughly.
Roughly.
Yeah.
So there is a space of vertex operators. There's no
Yeah.
particular, there's no puzzle, right?
There's no puzzle. There's no puzzle. You want that. You want that to be the answer that there's a non-trivial Hilbert space. There normally, okay. In string theory, we normally think that in target space there's a unique theory.
Yeah.
Right.
So that's the right way of quantizing some other theory there.
Right.
Right. Space of target space.
And here, I think the jump is that we're trying to define the target space theory in a way similar to the worldsheet theory is in string theory. So like in JT gravity, that's what's being done, right? You have all of these circles and they're filling in with all of these geometries and you're interpreting that as the 2D target space. That's where the confusion comes from.
Isn't it similar in string theory? We take these multi strings as the target space. Multi strings and they're moving around however they want. Isn't that? So I thought this multi-universe is very much like the target space, Fock space of string theory. Isn't it?
But the thing that we're adding is like on the world sheet, right?
Thing that we're adding. Yeah. Well,
I'm just saying the thing you're integrating over, that's like the word sheet, not the target space.
Yes.
In that sense.
Thing you're integrating over where were you
in the path integral, like we defined the inner product like that, right? Like
yeah.
I just mean the thing we were integrating over here.
Yeah. So we do the same in string theory, right? We integrate over string world sheets.
Yeah. So I just mean it's like the world sheet in that sense.
No, but in the end, your Hilbert space was that of multi world sheets. So it was like the target space Hilbert space.
String field theory.
String field theory.
In string field.
So I mean, your procedure should have led to string field theory. If we implement it.
If you do it with that path integral, it should lead to
string field theory is the target space Hilbert space.
Correct.
So though you do it with this world sheet, you're led to the target space Hilbert space. But it looks to me that this is like completely an example we understand conceptually very well, but I'm not seeing any puzzles then.
No, there isn't a puzzle there because there we do have a non-trivial Hilbert space.
And the thing is that there was no sense in which this alpha was states in a theory, right? Or whatever.
There's no sense in which alpha was theory.
There was a boundary theory.
Yeah. They were states in a theory, which is fine.
Yeah. There was no sense in which alpha was.
That's right.
This in string theory, I don't think of that as like a partition function of some group.
Yeah.
But maybe you should, like in these two-dimensional models, variable strings.
Yeah, maybe you should.
Yeah, but there the duality is with the world sheet. The target space is dual to some boundary.
In AdS CFT.
In this minimal string model.
Oh, the minimal string model is there. Yeah, okay. Yeah, you're right. I think the fact that that discretizes that.
Yeah, it's quite like
Usually we don't do this, but sure.
What would this equation be in string theory?
This equation, it would be like the product of all these vertex, like the overlap of all these vertex operators equals sum over intermediate states, I guess, like sum over all the different states. With
it is like a modularized space points, this alpha. Because that's how you do, right? You use an integral, right? So in that sense, you're integrating, maybe in some other basis. Effectively, that's that space, right? You can form a cross ratio space.
I guess we should think about
alpha would be much bigger.
Yeah.
The full like Fox, the full string field theory completes at space states. I know one part.
Yeah. So this was tree level. I was thinking tree level, but it's all the surfaces. Okay.
Yeah, all the stuff. Yeah.
So it's like a kind of a direct sum of conformed cross ratios.
No, but alpha was one particle. So I think you were right. There is just the one particle stuff.
Like the one particle Fock space, you mean?
Alpha itself was a one particle thing, right?
It's not a one particle.
It's not one particle, but the data is out of one particle. It's like
the data
is
out of one particle.
Like the choice of Hamilton.
I'm saying, what you do with quantum field theory, the analog of your Z, your alpha was like phi on state.
Yes.
Is phi number on state.
Yes.
So that has as much data as a one particle wave function, because phi is one function of variables.
Yes.
Now it's not exactly one particle state because you chose to use phi rather than creation.
Right.
But it's
similar data.
But one question is JT gravity. JT gravity, this matrix model expectation value is the same as the partition function of this but that's just one hyperbolizing surface, right? But if you
No, it sums over everything.
sums over everything, and that's the matrix.
Yeah, so it's actually to match the matrix model, it's very important. The important thing that SSS found was that to all orders of that expansion, including all genus, it's exactly the same as the matrix.
But this in principle gives you a way of computing the matrix model, right? For any sort of inner product. So let's say you
So if you had all
assume that all the G's are small, then
Yeah.
you can just do tree level
Yeah.
and just define the same thing at tree level and compute P alpha. That would be a different P alpha.
In practice, it's very hard, of course. Like the only model where we can do this directly from the path integral is Marolf-Maxfield. Even in JT gravity, doing that is kind of hard. Like SSS is basically that. And then anything more complicated than that, we have not done yet. So yeah, it's hard.
But in that
In
case, P
principle,
alpha
yes.
will be the measure of the SSS.
P alpha is the measure of it. It's exactly the matrix potential.
Sorry, but just following up on Utkar's comment. In string world sheet theory, you could perhaps generate the path integral over world sheets by some Feynman diagrams of some matrix model. And then you could call that the Hamiltonian or something.
Yes.
But it plays no fundamental role in string theory. I mean, the real quantization is target space.
That's how we interpret it usually. The change here in JT gravity was to interpret that Hamiltonian as the CFT Hamiltonian, like the AdS CFT.
Yeah, you can say what you want, but let's say I'm doing type 2B theory.
There you won't.
I know is what I'm after.
Yeah.
So, okay. Just to say that there was no puzzle.
There's no puzzle there. It's only if you try to interpret it as standard AdS CFT that it's a puzzle. Like as the target space path integral that it's a puzzle.
I'm really sorry I stepped out, but what is the puzzle?
The puzzle at this point is just, so we've gotten into the punchline here, which was that the gravitational path integral a priori computes a weighted sum over these alphas with some p alpha of these numbers, which you should think of as the partition functions associated with a given CFT, right? Which you would usually interpret in matrix or matrix model. Or different theories. So this alpha is the label, which is labeling the set of theories we're averaging over this ensemble. And the puzzle really is what is that, right? So in JT gravity, we know that this is labeling some matrix, which is the Hamiltonian of the boundary theory. And there we have a clear idea what it is, and it's a sharp thing, right? SSS already showed us that this is really what's being computed, and it's literally this formula. That's what makes you take this more seriously. The opposite point is how do you interpret this in, say, higher dimensions, where we believe that CFTs are pretty discrete and there's not that much to average over once you fix all the data. So what really is alpha in higher dimensions? Nevertheless, there are contributions which don't factorize. So there are wormhole contributions which connect different boundaries, and they would lead to this non-factorization, the factorization puzzle, which is the fact that the product ZZ is not the same as the product of Z's. So either it's the case that those contributions have to cancel in some smart way, in which case it's hard to see how you take them seriously, right? Like because they're getting cancelled by other stuff which we were ignoring and so on.
So for example, is the idea you might have such a contribution in the low energy gravitational path integral, but some UV contribution might cancel them. In the analog,
like the rough picture that people have usually is like if you want to compute the spectral form factor, which is a two-boundary partition function. Then we have a cylinder contribution that's there. And in very, very simple models, you can see that if you really want to talk about single instance, then there are some extra contributions which are called these half wormholes. And they look something like that. We don't have a very clear picture for there, but all of this stuff is added in such that it's the same as just the factorizing answer.
I mean, this they try to make precise Douglas's.
In a very, very tall model. That's the only picture where we understand it. But that's the picture. So that's a possibility that even in higher dimensions, something like other stuff cancel the contribution of this, such that secretly it was all factorizing anyway. In which case, the issue would be that we've gained a lot of mileage from using these wormholes. And if other stuff is cancelling it, you have to worry about how seriously to take that. That's the main puzzle.
Okay.
So it would come at the cost of losing a lot of progress.
Is it a puzzle? Sorry, just to understand, or is it more that, okay, maybe there are two possibilities. Either once you, even in the full gravitational path integral, you don't have these cancelling contributions. In which case it suggests that there's some generalization of AdS CFT. which has a gravitational dual where you have a bunch of CFTs that use sum.
Yeah. That's what I like about this formalism, which is it's agnostic to that the answer to that question. It says, let's just start with the path integral, define it in this way, a priori with connecting boundaries, contributions, and so on, not necessarily factorizing a priori. It leads you to this answer. So it's very generally, you're led to this answer where it's a sum over alpha. Now there's a detailed question, given the definition of the gravitational path integral, what is this set of alpha? It could be that there's just one alpha, in which case secretly everything was factorizing anywhere. We never needed to talk about wormholes if we were like careful enough. Or it could be that there's non-trivial alpha. That's a question that you can answer once you have a detailed path integral for that higher dimensional theory. And so it becomes an empirical question.
Can anything interesting happen if the net product matrix is defined in the beginning?
Yeah.
Is block diagram.
Is block diagram between these J's?
That's yes. Because I was just thinking in higher dimension.
Yeah.
All this gravitational path is difficult, but let's say the measure just is topological. The way around. I just can use some 3 manifold, right? So that may be my measure, let's say. So in that case, though, not all manifolds are null covariant. Right. Then equivalence classes, right? And the matrix elements will only be present in those equivalence classes and giving you a block diagram structure.
Right.
I'm wondering whether that
maybe that forces you to non-trivial alpha. I'm not sure. It seems like that would force you to non-trivial alpha because block by block you can do this, right?
Yeah. Get some
sounds like that would at least
different structure, right?
At least the different classes will become different orthogonal alpha.
Yes.
So it sounds like you would have alpha. So this is
like
related
sums of alpha.
Yeah. So this would be related to this fact. Even here, the alphas are orthogonal anyway.
No, that's alpha, but there is another alpha for the other block, another alpha for the other block.
That whole set is alpha.
No, but I'm using this block diagram structure because this alpha from one universe doesn't talk to the alpha of the other.
That's also true here, right? Because if you take the overlap between alpha 1 and alpha 2, any number of C's in circle, that's still 0.
Okay.
Right? So it is block diagonal in that sense.
Yeah, but
I think what you're saying is
this block diagonal that I talked about that we are not anticipating.
Here, I think it would be the opposite. So any choice of alphas would have to be block diagonal. I think what you're saying is if I find something in the path integral that is block diagonal, then I think it would imply that there are non-trivial alphas.
Yeah.
So I think that's what's going to end up happening. And that's related to this comment that, so of course, different words it has been said that because of AdS CFT, we should believe that there is no non-trivial alpha. And that gets related to this cobordism conjecture for the reason you said. Because if you can have things that are not cobordant, then you would end up having alpha. So if to really say that alpha is just one, you really need things connecting arbitrary boundaries.
And so this gives it a more robust.
Yeah.
Because it doesn't depend on the details.
It can depend on the details.
Like of non-trivial.
Right. Like in string theory, we have
the fact that it's not many equivalence classes can tell you that there has to be some
correct. So,
but then the upper modes have to kind of
correct. So you need some extra ingredients which will make the cobordism.
I just wanted to ask you guys, what is the plan? Because we shouldn't rush Pratik, right? But